Hi, I'm Tom Beebekauser with Wetland Restoration and Training. Thanks for joining us today. Our topic of today's video is the control of head cuts. What's a head cut? You're looking at one right here. A head cut is a waterfall, and the waterfall is moving over soil and not necessarily rock. Now this head cut is being slowed down by the roots you see here. But what a head cut does is it moves upstream and it causes a deepening and a widening of the ditch or the stream channel, and it results in eliminating standing water on the landscape, and it lowers the elevation of groundwater. What does that mean? It destroys wetlands. So I'm going to be showing you how to control head cuts, which is an important aspect of wetland restoration. So stay tuned. We're going to see how this is done. This head cut is draining a massive wet meadow wetland at high elevation in Nevada. This wet meadow in Nevada does not have a stream channel with a bed and banks. This is how most natural wet meadows appeared before they were drained by ditches with head cuts. Water flows over the surface of the ground in a sheet-like pattern. The soil is saturated with organics that overlay clay. It's rare that you'll find a wet meadow wetland like this one that has not been drained with ditches. This head cut formed when someone dug a ditch downstream in the valley to drain a wet meadow so it could be cut for hay. This head cut is carving a deep ditch that is lowering the elevation of groundwater as it moves upstream. This head cut is unzipping the huge wetland as it moves up the valley. Multiple head cuts have formed, with each one carving a deeper and wider ditch as they move upstream. Walking downstream, we see a river of water being drained from the wet meadow wetland. This stream channel is located downhill from the wet meadow wetland we've been looking at. The artificial stream was formed by multiple head cuts advancing through the wet meadow. Note how grasses, not sedges, are growing on the left side of the ditch. These grasses are growing on the well-drained soil that was previously wet meadow wetland. The exposed roots in the channel show that erosion is taking place. The erosion is caused by head cuts advancing into the wet meadow. The head cuts are causing a deepening and a widening of the channel. The water flowing in the stream channel is from the large area of wet meadow wetland that's being drained. This site is downstream from the wet meadow wetland. The area used to be wet meadow. Historically, there was never a stream channel with bed and banks at this location. The stream channel was formed by head cuts advancing through the wet meadow. The deep and wide channel is now a ditch that is draining this historic wet meadow. Walking further downstream, we see where head cuts have cut a deep and a wide channel through what was once a very large wet meadow. The land on either side of the channel is dominated by sagebrush, a species that grows on dry ground. It's difficult to believe that this arid zone was once part of the wet meadow wetland. This canyon is found within walking distance downstream of the wet meadow wetland. The canyon was formed by a progression of head cuts advancing through the wet meadow wetland. The water in the stream channel represents the elevation of groundwater. The water you see in the stream channel has been drained and pulled out of the historic wet meadow wetland. This photo shows high vertical banks downstream of the wet meadow wetland. One can see the dark colored soils from the historic wet meadow wetland in the stream bank above the heads of these individuals. The highest banks are located the farthest downstream of the wetland that's being drained. It would be difficult and costly to restore this wet meadow wetland. A head cut can destroy a wetland overnight, and it can cause tremendous erosion in the process. You're watching water flowing in a temporary ditch we dug to drain water for the construction of a wetland. Riffles can be seen where the stream is flowing over rough places in the bottom of the ditch. These rough places, which are also called nick points, are triggering head cuts to form that will be visible once the water in the ditch dries. Head cuts form rapidly and get worse in a hurry. This head cut is one of many that formed in a newly restored stream in Yosemite National Park because the stream was not designed or built using techniques that are proven to prevent head cuts from forming. The head cuts that formed in this ditch have drained a wet meadow on the Monongahela National Forest in West Virginia. The bottom of the ditch is gravel, and the groundwater that was present in the gravel is being pulled into the ditch. This massive head cut formed after a ditch was dug along the base of the mountain to divert a small stream. The stream was moved and channeled to dry the wet meadow so it could be cut for hay and so livestock would not get stuck in the mud. Notice how the ditch is narrow and shallow uphill of the head cut. The canyon created by the head cut is draining the entire wet meadow. I would like to show you how culverts stopped a major head cut from moving upstream. Looking downstream, we see that the head cuts have eroded a deep and a wide channel in this valley that's located along the Harvest Road near Sonoyta, Arizona. Notice how the stream banks are vertical and eroding. The head cuts that started downstream have worked their way upstream to the road. Cows have eaten most of the plants in the channel and the floodplain downstream of the road. Let's walk across the road and look upstream. Here's how the drainage appears on the other side of the road, looking upstream of the culverts. The drainage is a beautiful and a diverse wet meadow wetland. Look at the wide floodplain with no stream channel and no erosion. The culverts have provided permanent vertical grade control, protecting the wet meadow upstream of the road by not letting the head cuts move under the road. I have seen where traditional culverts have stopped head cuts from moving upstream. This is why one should use great caution when replacing a culvert with a bridge or a bottomless culvert. The last thing you want to do is to provide conditions where a head cut can move under the road and destroy the wetlands upstream of the road. This profile view shows a wetland not affected by a head cut. There is water standing on the surface, and the elevation of groundwater is also near the surface. The soil is saturated all year because there are no head cuts in ditches that would drain water from the wetland. This is the same wetland that is being drained by a head cut. The head cut has carved a deep channel or a ditch through the wetland. The channel has eliminated surface water and has lowered the elevation of groundwater. Additional head cuts can be expected to advance in the channel that would further dry the wetland. There are two main ways to control a head cut using rock. The first way to control a head cut is to use the slope and armor technique. The slope and armor technique can be used where the vertical face of the head cut is less than 2 feet, and there are no head cuts in the drainage downstream that could advance and destroy the head cut that you're repairing. The second way to control a head cut is to use the vertical grade control technique. This involves building a rock structure across the floodplain that extends deep into the ground. The technique is used where the vertical face of the head cut is over 2 feet and there are head cuts located downstream that will not be controlled by your project. This drawing shows a typical profile view of a head cut controlled using the slope and armor technique. The step of the head cut has been sloped and armored with rock to control erosion. Here's a plan view showing the slope and armor technique for controlling a head cut. A wide floodplain was shaped for the stream. Rock is embedded in the ground across the width and the length of the floodplain. Soil has been spread over the rocks so plants will grow. This drawing shows a profile view of the vertical grade control technique that's used to control a head cut that has a vertical face greater than 2 feet and where other head cuts are located downstream that will not be controlled by the project. Rock has been buried in the ground that is deep enough so that the other head cuts advancing upstream will not undermine the vertical grade control structure being built. The vertical face of the head cut has been replaced with a sloped ramp that is made from rock. Here's a plan view showing how the vertical grade control technique is used. A channel has been dug across the 100-year floodplain of the ditch or stream that is also keyed into the banks. Rocks have been placed in the channel that are compacted tightly together. The valley and the floodplain are shaped so that water must flow over the rock. The rock is covered with soil so that plants will grow. The elevation at the base of the vertical grade control structure you're building must be the same or lower than the elevation of the top of the closest permanent vertical grade control structure located downstream. The reason is that head cuts located downstream will advance upstream, eventually reaching the vertical grade control structure that you have built. Your structure will fail if it does not have a foundation that is deep enough in the ground and sloped with a large and gradual wedge of rock so it won't collapse when the head cuts reach it. The rock used to build a vertical grade control structure and to armor a slope should be from 6 to 12 inches in diameter. The rock should be angular or fractured so it fits tightly together like the pieces in a puzzle. It's best if the rock is not washed clean and contains fines so it can be compacted. Here the excavator operator has mixed soil in with the rocks to fill spaces between the rocks. The bucket on the excavator is being used to pound the rock into the ground so it will be locked together and not move during a flood. This rock is too clean to use in armoring a slope or building a vertical grade control structure. It would be better if smaller diameter rocks and fines were mixed in along with soil so water would not flow between the rocks and cause erosion. This head cut behind me has a vertical face of 4.5 feet. That means we'll have to control it using the vertical grade control method. We're not going to be able to slope it and rock it using the slope and armor method. The Dye Ranch Erosion Control and Wetland Improvement Project was completed in 2024 near Payson, Arizona. It was completed on land managed by the Arizona Game and Fish Department. The main purpose of the project was to stop erosion by taking action to control head cuts that were causing the erosion. The project was also designed to restore wetland pools for a diversity of wildlife species, including providing habitat for the northern leopard frog, a species of greatest conservation need in Arizona. The head cuts that were present in the valley were draining historic wetlands and causing erosion. The soil washing downstream from the head cuts was filling the shallow wetland basins that were present. We plan to control the head cuts along a 1-mile stretch of the ephemeral stream on the Dye Ranch by using both the slope and armor technique and the vertical grade technique. To comply with water rights regulations, we followed direction that the project could only be implemented if no water was impounded and the size of the wetlands was not increased. Let's see how one of the head cuts was controlled on the Dye Ranch by using the vertical grade control technique. I used blue-colored plastic ribbon to show Don Smith, the excavator operator, where to dig for building the buried vertical grade control structure that was needed to control the head cut. Don began digging a trench that was perpendicular to the flow of water in the drainage. The lower edge of the trench followed the vertical face of the head cut. The trench was dug to span the width of the 100-year floodplain so that rock could be keyed into the banks and not simply placed on the surface of the ground. He piled the soil that was removed so it could later be used to cover the rock and to shape gradual banks on either side of the trench. The bottom of the trench is dug so its elevation will be the same or lower than the elevation of the top of the nearest buried vertical grade control structure we're building downstream. We're using the excavator to dig a trench instead of a backhoe or a dozer because we want to minimize soil disturbance in the drainage. We purchased the rock needed to build each vertical grade control structure from a nearby quarry. We ordered angular rock instead of round rock because it would be easier to make the rocks fit tightly together. The rock was delivered in large dump trucks. The truck drivers had to dump the rock near the road because there was a danger of them tipping over if they tried to drive off-road to dump the rock near where each structure was being built. The rock they brought us was large in diameter. There were no smaller rocks or fines mixed in. We did not need rocks this large in diameter, but this is what the company delivered to us. Here is Ethan Sandoval with Bat Conservation International. Ethan drove the large wheel loader we rented to move the rock from where it was dumped to each head cut we planned to control. Ethan was able to scoop up the rock with the bucket on the wheel loader and bring it to each trench that we dug. It would have taken us weeks to move this rock using the small excavator. Don uses the bucket on the excavator to move the rock into position and to shift the rock so it fits tightly together. The surface of the rock is shaped to match the slope in the valley at this location. A shallow dip is placed in the center so that water will flow over and not around the rocks. The bucket is used to compact the rock tightly together so there are only small gaps between the rocks. You can see how some of the rocks are pushed down 6 inches or more when pounded on with the excavator. Don takes his time and is very thorough in fitting and shaping the rocks so they won't settle. Don spreads soil over and between the rocks. The soil is pushed into the ground to fill voids between the rocks. The soil was also placed over the rocks so plants would grow and so that water would flow over the top of the rocks instead of leaking down into the trench. Don uses the excavator to move the soil that was saved to shape gradual banks over both sides of the rock structure. The ends of the rock-filled trench are then covered with a thick layer of soil that is shaped so that water flows over and not around the rocks during a flood. Don moves over to the other side of the valley to shape a gradual bank of soil over the end of the rock-filled trench. He rakes and loosens the soil so that water will flow over the buried vertical grade control structure in a sheet-like pattern. Notice how soil has been spread and shaped in the valley so the flow of water will not be concentrated in a narrow channel over the structure. Don uses the blade on the excavator to spread the remaining soil that was removed when the trench was dug for the rock. He is also spreading soil over the rock to hide the rock from view so the valley will look natural. The crew uses rakes to fill voids between the rocks with soil and to break up large clumps of soil. The hand raking is important because the surface of the ground can be adjusted so that water flows over the rocks in a sheet-like pattern and does not cause erosion. The project turned out better because of the final landscaping that was done by hand. Here's how the repaired head cut appeared 3 months after construction. We should have filled the hole you see between the rocks and the grass during the construction of this vertical grade control structure. This is because we later observed water flowing from the surface into the space between the rocks and the edge of the channel. It was an easy fix. We used a shovel to place soil in the hole and compacted the soil with our boots and the end of the handle on the shovel so water would flow over the surface and not into the rocks. Here's one of the series of small head cuts we decided to control using the slope and armor technique. Ethan used the wheel loader to pile the rock needed to armor the slope before construction. Don Smith will use the slope and armor technique to control these head cuts. Don slopes the vertical banks with the excavator. He uses the soil that is removed to fill in the washed out holes in the drainage. Some of the soil that is removed is placed in piles. This soil will later be used to form the stream banks along the edge of the rock that we place. Don shapes a wide floodplain with gradual slopes where the head cuts were located. The valley is dug deeper than the planned final elevation. This is done to make room for the thickness of rock that we placed to armor the slope. Rock is placed on the exposed soil within the reshaped floodplain of the stream. The rock is placed in the channel and up the sides of the stream banks. Don uses a digging bucket with teeth to place the rock at a layer about 12 inches thick. He works to maintain a shallow valley on a gradual slope with a wide floodplain so that the water will spread out and flow over the rock in a sheet-like pattern. He uses the weight of the machine to push the rock into the ground. This is difficult to accomplish because the rocks are large and the ground is compacted. Don works to taper the outer edge of the floodplain and to fit the rocks tightly together. He also begins covering the outer edge of the rocks with soil to form gradual stream banks. Here's how the head cuts that were repaired using the slope and armor technique appear 3 months after construction. The head cuts have not reappeared and the armored slope is not eroding. This drawing shows how a groundwater dam and the slope and armor technique can be used to restore a wetland that's impacted by a head cut. A groundwater dam was constructed across the spillway or the outlet of the wetland. The vertical face of the head cut was then sloped. The surface of the groundwater dam and the spillway were armored with rock that was embedded into the ground to control erosion. Water leaving the wetland will now flow over the rock. We use both the slope and armor technique and the groundwater dam technique to restore 4 wetland pools impacted by head cuts on the Dye Ranch. Sediment was washing downstream from the head cuts that were located upstream. Soil that was high in clay had largely filled the wetland basins. After many years of drinking from the wetlands, cows had compacted the clay that had washed into the wetland basins. The compacted clay was acting like a lid to prevent groundwater from rising to the surface. The clay was compacted by livestock walking in the wetland basin when it was dry. The groundwater that historically supplied the wetland with water was no longer able to rise to the surface and fill the wetland. Another problem was that the head cuts in the valley were advancing upstream and would soon enter and destroy the sediment-filled wetland basins. An important action of the Dye Ranch project was to restore the wetlands by using the slope and armor technique to control head cuts and the groundwater dam technique to return water to the dry basins. A groundwater dam was built across the outlet or spillway of each wetland being restored. The head cuts located in the spillway were sloped and armored with rock. The surface of the groundwater dam and the length and the width of the spillway were also armored with rock to prevent erosion. Don Smith begins the restoration of this wetland by digging a core trench perpendicular and across the floodplain of the dry stream. The pink wire flags mark the lower edge of the trench to be dug. The wheel loader placed the rock next to the trench so it could be used to armor the spillway to prevent head cuts from forming. The purpose of the core trench is to interrupt permeable layers of soil, replacing this permeable material with soil that is high in clay and compacted in layers. The trench begins at one side of the valley at an elevation that is equal to or higher than the estimated water level in a 100-year flood. The trench is dug through vegetation, organic soil, and the compacted clay near the surface. Don digs the trench deep enough to cut through a permeable layer of gravel that's carrying water underground. I ask him to dig even deeper until he keys into a thick layer of saturated clay from 8 to 10 feet below the surface. He saves the soil that's high in clay in a separate pile and will later place this clay in the core trench to make a groundwater dam. The soil Don is removing is wet and muddy because this is where the water is flowing underground. You can see and hear the excavator bucket hitting rocks in the soil, which shows us the layer is permeable. Don begins filling the core trench with soil that's high in clay. You can see the water collecting on the bottom of the core trench. This is a sign we have dug deep enough to cut through the permeable layers of soil that are carrying water below the compacted clay on the surface. If you wait too long to fill the core trench with soil, the trench will fill with water. Once it fills with water, it will not be possible to compact the clay that's placed in the core trench. This is because the soil will turn to mud and you can't compact mud. Don spreads each bucket of soil he places in the core trench in layers about 6 inches thick. He compacts each layer using the back of the bucket on the excavator. This is a slow but important process. The result is that the historic elevation of groundwater in the valley will be restored and the wetland basins will once again contain water. We're only building this groundwater dam from 3 to 4 feet wide. If you take shortcuts in building the groundwater dam this narrow, it won't do what you want it to do. Don continues to use the excavator to fill the core trench with layers of clay, using care to compact each layer of clay so it will hold water and not leak. Digging the core trench goes fast, while filling it takes a long time. Building a groundwater dam is the most effective and lowest cost way to restore water in a dry wetland, especially in an arid region. Here Don has dug a borrow pit to come up with enough clay to fill the core trench that's needed to build the groundwater dam. There are 2 reasons why he needed more soil. The first is that the permeable soil he removed contained gravel, rock, and sand. We don't want to place this permeable soil back in the core trench. The second is that he's compacting the clay returned to the core trench, and this is going to reduce the volume by 50%. Don is also compacting the clay by running over each layer with the excavator. Don now compacts and shapes the top of the groundwater dam so that it's the same elevation as when we started the project. We are careful not to build an above-ground dam that will impound water. He makes a wide floodplain with gradual side slopes and no defined stream channel. We left room to place and embed rock over the groundwater dam and to armor a slope so there won't be any head cuts in the future. We begin moving the piled rock over the groundwater dam. The rock is placed to armor the top of the groundwater dam, which is the entrance to the spillway and is also the wetland outlet. Don will travel over the rock to push it into the ground and will rearrange the rocks so they fit tightly together. We're moving rocks from where they are piled up on the slopes of the valley so floodwater won't cut a channel around the rock. These rocks will also be pushed into the ground so they don't wash downstream during a flood. Here Ethan is using the wheel loader to embed rocks in the inlet that we built for a restored wetland. I asked Ethan to use the wheel loader to drive over the rocks we placed on the higher and drier ground. The heavy weight of the machine on rubber tires is better able to push the rocks into the ground compared to using the excavator. We kept the wheel loader off the groundwater dams and the spillways where we did not want elevations lowered. Now that the groundwater dam is built and the spillway is armored with rock, we work on removing the cow manure and the clay that have accumulated in the wetland basin over the past 100 years. The wetland basins are shaped to their historic size and are given gradual slopes. The fence that was erected around the dry ranch property will keep out livestock which are grazing on the surrounding National Forest System land. We spread the soil that was removed on higher ground on either side of the restored wetland. Don Smith prepares the ground for seeding and planting by using the rough and loosen technique. Rain will soak into the ground and there will be no erosion because the compacted soil has been loosened. The loosened soil will also provide superior habitat for mice and voles because these have difficulty digging burrows in soil that's compacted by cows and horses. Once the organics and the clay were removed from the basin, we began armoring the inlet to the wetland. This is done to prevent headcuts from forming where water flows down the slope into the wetland. One major benefit of using rock to armor the inlet, the groundwater dam, and the spillway is that elk, horses, and cows will not be able to destroy the wetland by causing new headcuts to form. The large clumps of sedge plants that were saved when the wetland basin was restored were replanted using the excavator. The sedges were replanted at elevation equal to the elevation at the entrance to the spillway. This was done so the plants would grow in saturated soil along the water's edge. The smaller clumps of sedge were planted by hand along the water's edge in the restored wetland. I used the laser level to take an elevation reading at the entrance to the spillway. I then used the laser level and the survey rod to place wire flags at the planned water level in the restored wetland to serve as a guide for planting. Soil was raked by hand to cover the roots of the sedges so they would grow. Marks left by the excavator bucket and the excavator tracks were also raked out by hand. Within 1 day of construction, the restored wetland had filled with water. Here's how the wetland appears 3 months after construction. Quamachin Lake is a beautiful place to visit on Vancouver Island in British Columbia. The people who live on Quamachin Lake were very concerned about the algae blooms in the lake and how sediment was filling portions of the lake. I was invited to work with members of the Cowichan Land Trust to reduce erosion at Quamachin Lake. I was shown a stream that was historically moved and channeled into a ditch to drain land for farming. The stream was actively eroding and transporting large quantities of soil into Quamachin Lake. The erosion was obvious by the vertically exposed soil along the banks and the shrubs and trees that were falling into the stream. We observed many headcuts in the ditch. We designed a series of wetlands to build along the ditch. The wetlands would be built to capture soil before it entered Quamachin Lake. We could only build the wetlands on the right side of the ditch because a different individual owned land on the other side of the ditch. I placed the wetlands along the ditch every 2-foot change in elevation. Dams were not built across the ditch because this would have flooded the neighboring property. The soil to be removed from digging the wetland basins would be spread along the outside and downhill edge of each wetland. The spillway for each wetland was the section of ditch that was left in between each wetland. The elevation of the bottom of the ditch would become the elevation of the spillway for each wetland being built. A series of headcuts were present in the ditch where the wetlands would be built. Looking back, we should have measured the quantity of soil moving in the stream. We didn't do this because of the lack of funding, because no one wanted to delay the implementation of the project. We designed 4 wetlands to be built in a drained field that was dominated by reed canary grass. The orange-colored plastic ribbons marked the perimeter of one of the wetlands to be built. An excavator was used to build the wetlands. Each wetland was built by digging a large basin that was deepest in the middle. Water flowing in the ditch would enter and leave each wetland basin. I was concerned that digging the wetlands would cause additional headcuts to form and that the soil washing downstream would quickly fill the new wetlands. To control erosion, we constructed a buried vertical grade control structure across the ditch, and this was done where water entered each wetland, and then we sloped and armored the outlet or the spillway for each wetland. We also built a groundwater dam across the ditch at the lower edge of each wetland being built. The rock needed to build each vertical grade control structure was delivered by dump truck. The dump truck was able to unload the rock close to the structure being built where the ground was dry and firm. In some cases, the dump trucks unloaded the rock further away from the vertical grade control structure being built, and this is because the ground was soft and there was a danger of getting stuck. We then had to use the excavator to move the rock 1 bucket at a time. We used angular rock of mixed diameters ranging from 15 to 40 centimeters to build the structures. We requested that the rock contain fines and smaller rocks so it could be compacted. Here the excavator digs a trench across the 100-year floodplain of the ditch. This is done where it will enter the new wetland. The trench is dug where the head cut was found in the ditch. The bottom of the trench is dug to be the same elevation as the planned top of the vertical grade control structure being built downstream at the inlet to the next wetland. The excavator places rocks in the trench that has only been dug on one side of the ditch. The excavator will move over to the other side of the ditch to finish digging the trench for the rock. The trench that was dug across the floodplain of the ditch is filled with rock. The tilt bucket on the excavator is used to arrange the rocks so they fit tightly together. The rocks in the trench are compacted using the bucket on the excavator. The excavator now digs a trench on the other side of the ditch. This trench is dug at right angles to the flow of water in the ditch. The end of the trench is dug into the bank of the ditch that is equal to the elevation of water during a 100-year flood. The bucket on the excavator is used to place rock in the trench. The rock is angular and of various sizes, and it contains fines so it can be compacted. The trench is filled with rock and compacted. The excavator shapes a slope or a ramp downstream from the rock that's placed in the trench. This slope is armored with rock that is pushed into the ground. The rock in the vertical grade control structure and the ramp is compacted and pushed into the ground. It is of critical importance that there is no drop-off within the area that's marked by the dashed line. Another head cut will form if there is a drop-off. The pile of soil is now spread over the rock. Soil is not spread in the very bottom of the channel to reduce the possibility of erosion. Water in the ditch will enter the wetland by flowing over the rock that's placed in the buried vertical grade control structure. Water will not be able to flow around the rock and cause erosion, even in a flood. The wetland spillways were widened, sloped, and armored with rock so they would not erode and form head cuts. The rocks used to armor the spillways were pushed into the ground using the bucket on the excavator. This photo shows one of the spillways with water flowing from the wetland into the ditch. Here water is flowing over a buried vertical grade control structure into the most upstream wetland we built. The red arrow points to sediment that's settled in the new wetland. The wetland filled with soil after only 2 years of construction because of the great amount of erosion taking place upstream. We had to remove the soil using an excavator and a dump truck. The buried vertical grade control structures have controlled the head cuts and have prevented new head cuts from forming. Much of the area where we spread the soil has become wet meadow wetland. A diversity of plants are growing in the wetlands. The wetlands are attractive features on the landscape. You're likely to find head cuts like this one wherever ditches were dug to drain wetlands. Head cuts moving upstream made this ditch much wider and deeper over the years. This ditch is lowering the elevation of groundwater in the valley. It's very tempting to try inexpensive ways to control head cuts instead of paying for rock. Here's where plastic was placed over a head cut in an attempt to stop the erosion. Water flowing over the plastic has carved a deep pool at the base of the head cut. This deep pool will soon undermine the plastic and allow the head cut to continue upstream. Notice that the flow of water has been deflected and it's now eroding a much wider head cut on either side of the channel. I've found that it's not possible to control a head cut by using plastic or geotextile. The permanent solution is to restore the streams and wetlands and then to install buried vertical grade control structures across the floodplain of the stream where head cuts are located. Here's where someone used plastic to armor the base of a riffle and vertical grade control structure in a ditch they tried to make look like a stream in northern Kentucky. The pool doesn't hold water and the rock and gravel they placed in the plastic has washed downstream. This silt fence with some rock thrown in the ditch was not able to stop the head cut near Lebanon, Virginia. The best way to control a head cut and to stop erosion is to use rock. This head cut formed in a small ephemeral stream on our farm in eastern Kentucky. The head cut began after we used a dozer to level an area where we built our barn. The dozer operator dug a shallow ditch along the base of the hill to divert water flowing in the ephemeral stream so our barn would not flood during a heavy rain. The ditch is called a diversion ditch because it diverts water around a structure or field. The ditch cut a slice out of the floodplain and channel of the ephemeral stream. The vertical drop-off created by the dozer quickly became a head cut that moved up the valley during runoff events. The stream only carries water 2 or 3 times a year, But each time the stream flows, the head cut becomes deeper and wider and moves a little bit more uphill. Notice that there is no stream channel with bed and banks upstream of the head cut. You can't even see water flowing in the stream up valley from the head cut. The water has been flowing in a sheet-like pattern over the floodplain of the natural ephemeral stream. Large amounts of soil washed downstream from the eroding head cut after each flood. The soil was settling in the ditch behind the barn where it flowed over a gradual slope. I had used a shovel to remove the soil that settled in the ditch from the head cut several times a year to keep the stream from flowing into our barn. 10 years after our barn was built, we hired John Utterback to control the head cut, and he did this by installing a buried vertical grade control structure made out of rock. John had to remove a large oak tree so he could access the head cut behind our barn with his excavator. John dug a deep trench across the face of the head cut that keyed into the banks on either side of the stream. We filled this trench with angular rock from 6 to 12 inches in diameter, as shown by the red dashed rectangle. Here John is using a skid steer to move the rock to where we were controlling the head cut behind the barn. John used the excavator bucket to place the rocks in the trench and to pound them into the ground. He sloped the vertical face of the head cut and formed a ramp for water to flow over the steep ground. He also placed soil over the ends of the rock-filled trench to form stream banks. I hand-placed many of the rocks because it was not possible to do all of the work with the excavator. I then used a rake to shape the new stream banks and smoothened out the floodplain so there would be a sheet flow of water over the rock. Here's water flowing over the rock we used to build the vertical grade control structure 3 years after construction. The ephemeral stream is flowing after we received 1.7 inches of rain one morning in February. Notice how the piles of leaves are creating braided channels in the stream. The good news is that the head cut was controlled by the project with no new head cuts being formed. The bad news is that there's still a need for maintenance to keep our barn dry. This is because leaves washing downstream collect in the ditch that's nearly level along the base of the hill. The leaves will pile up, blocking the ditch and diverting the flow of water into the chicken pen next to the barn. I suggested to my wife that we could change what we're raising to ducks and not chickens. Here's where we controlled a head cut in a stream following the removal of a dam near the community of Trail in British Columbia. We placed rock from a quarry in the trench and then covered this rock with natural-looking creek rock. We made this riffle on top of a buried vertical grade control structure that we built to control a head cut in the stream, also in British Columbia. We built this vertical grade control structure to prevent head cuts from forming after removing a dam at a stream outlet to Violin Lake in British Columbia. This eroding and unattractive ditch is located at Lindsey Wilson College in Columbia, Kentucky. Head cuts were causing significant erosion, and the stream was a real eyesore on campus. The stream and valley were located on a steep slope with a large watershed. It would have cost a lot of money to install a series of vertical grade control structures or even to slope and armor the valley with rock to control these head cuts. At the time of this project, I had just started working with Dr. Arthur Parola Jr., Professor of Environmental and Civil Engineering at the University of Louisville Speed School of Engineering. I showed Art photographs of the site and asked for his advice on what to do. Art Parola saw that there was limestone bedrock in the bottom of the eroding stream channel. He suggested that I use an excavator to remove the soil that was likely to erode down to bedrock, then to create a wider floodplain, and then to slope the banks so they would not erode. I remember him saying that we could control the head cuts and the erosion if we simply removed the soil that was eroding and placed it on higher ground. Art's suggestions were brilliant. It was an easy decision to follow his advice. We hired expert stream and wetland builder Ferris Osborne by the hour to provide and operate the excavator needed to complete the project. We began work by removing and saving the little topsoil that was present. The next step was to remove the soil that was eroding down to the limestone bedrock. Here we're making a much wider floodplain that is level in cross-section so that the water will flow in a sheet-like pattern, saturating the soil and creating conditions for wet meadow wetlands to develop. We temporarily piled the soil on higher ground and would later spread it to blend in with the surrounding landscape. The excavator dug down to limestone bedrock along the entire length of the stream. This was not easy because the steel bucket would catch on the large boulders and shake the machine and the operator. We removed as much soil as possible that was on top of the rock. Had we left a layer of soil over the rock, it would have eroded. Due to the uneven surface of the bedrock, it was not possible to scrape the floodplain clean like a tennis court. We did not dig a narrow channel for the stream with a bed and banks. Instead, we made a wide floodplain that was also the stream channel, and this was done to reduce shear stresses and the possibility of erosion. Large rocks were picked up and saved to place on the finished floodplain. After the soil was removed from making the floodplain, we shaped gradual slopes along the stream banks. We then placed the large rocks that were saved on the floodplain to provide habitat for animals. Ferris Osborne strategically placed the boulders so they would look natural in the shallow holes he had dug in the floodplain. The few pieces of woody debris that were available were also placed on the floodplain. The next action involved spreading the soil that was removed on higher ground and then shaping the soil so it would look natural. The topsoil that was saved is spread over the restored floodplain of the stream. The topsoil is mixed with plant roots and then spread rough and loose on the floodplain to increase plant diversity. We sowed the exposed soil with wheat and mulched using straw to control erosion and to promote the germination and growth of plants. Covering the ground with straw also helped to gain acceptance for the project by removing the shock of seeing so much exposed soil. We anchored straw bales across the floodplain just in case there were heavy rains with significant runoff before the plants and the roots could get established to prevent erosion. Here's how the stream appeared at the end of the day. 30 days later, the restored valley was attractive with wheat and grass that were growing. The head cuts and erosion were controlled at a reasonable cost by building a large floodplain that was armored with rock that was already in place below the surface. You can see that it's very important to control head cuts because head cuts destroy wetlands and streams. It's very possible to control head cuts using the techniques that I've described in this video, and it is well worth your time and money doing this. Well, I'm Tom Beebekauser with Wetland Restoration and Training, and invite you to subscribe to this video series and to mark that you like it, and please share it with others, and I wish you every success in controlling head cuts and restoring wetlands and streams.